Hello, can you guys hear me now? I'm using push to talk now. Yeah, if you can hear me, can you type in the chat so I know it's working? Okay. Okay, so it seems this Discord channel only allows me to use push to talk, so I have to keep holding a key on the keyboard in order to talk. So let's see. Let's see if our mods can fix this, but otherwise then let's get started. Okay, so the how many? Oh, we have 22 people. That's pretty great. Okay, so the intention of this session is twofold. First of all, you guys can learn about Mars protocol. You can learn about smart contract programming. On the other side, for me, I can help you guys look at my code and perhaps spot some bugs. So that's the intention here. In terms of scheduling, for now, I'm thinking about doing 3 sessions. The first one we go over the airdrop contract. The second one we go over the builder vesting contract, and the third one we made some modifications to the Cosmos SDK regarding how fees, the protocol revenues should be distributed. So that's a custom logic injected into Cosmos SDK. That will be a short session, but let's see. We can do that if we have good results, good reviews for the first 2 sessions. Okay, so let's get started with the airdrop contract. So our airdrop compared to other airdrops that has been conducted on other chains is a bit more complicated, and that the core reason for that is that Terra uses a non-standard BIP44 coin tap parameter when converting seed phrases into public keys and addresses. So that was a lot I just said. So let me break this down a bit. So BIP39 is a Bitcoin improvement proposal, which is equivalent to ERC if you come from the Ethereum world. So BIP39 defines an algorithm to convert your mnemonic phrase into your private key, public key, and account address. So this algorithm involves a few parameters. So if you change this parameter, you get a different public key, private key from the same seed phrase, right? So the intention of that is the idea that people don't want to memorize 100 different seed phrases. They want to have just one seed phrase, and you can generate many accounts with that same seed phrase for different purposes. So among those parameters, one is called the coin type, which, as the name suggests, is the type of coins. Like you may have Bitcoin as one coin type, so Bitcoin gets a number of 1. The second, you may have a Litecoin, which gets a number 2. Number 3, I think, is Dogecoin, but I could be wrong. But anyways, so if you have the same mnemonic phrase and you have a different BIP44 coin type, you get a different account generated from the same seed phrase. So I just said BIP39 is the algorithm. BIP44 is another Bitcoin improvement proposal that defines the list of coin types. So Bitcoin is 1, Litecoin 2, Dogecoin 3. So BIP44 is basically a huge spreadsheet that records the coin types and their corresponding numbers. So Cosmos is number 118. But however, we know Cosmos is not one chain or one coin. It is an ecosystem of many chains and many coins. So most of these chains, most of them, by default, simply uses the Cosmos coin type, which is 118. So this includes Osmosis, Cosmos Hub, Akash, etc. However, there are a few other chains that became creative and have their own BIP44 coin types. Some of them have good reasons, such as Secret Network, because they want privacy. The others don't have very good reasons, and that includes Terra. So Terra uses their own BIP44 coin type called Terra, which is number 330. So the result of that is you have the same seed phrase. You import that into Terra Station wallet. TerraStation will generate an address based on coin type 330. But if you import the same seed phrase into Kepler, Kepler will generate an address based on coin type 118, which is the Cosmos coin type. And that is a different account than what you get with TerraStation. And that causes a problem. So let's say we are doing Mars token airdrop, right? So there was the so-called Mars Classic token on Terra Classic. We took a snapshot of that. And from the snapshots, we generate a list of user addresses and their eligible airdrop amounts. So let's say this Terra account, this Terra address entitles this much Mars token, this Terra account entitles that much Mars tokens. But our airdrops are going to be conducted not on Terra, but on Mars chain. And Mars chain uses coin type 118. So the thing is, those Terra users, they import their Terra seed phrases into Kepler wallet. They don't see their Terra address, right? They see their Mars address, and it's not a simple Mars address, it's a completely different Mars address. And that causes an UX issue because users cannot generate their original Terra address inside Kepler wallet, right? Okay, it seems the voice is fixed. Let me try if it works. Can you guys hear me now? If you can you type something in the chat? Hello. Okay, perfect. I can finally release my finger from the keyboard. Okay, cool. So you might ask, why doesn't Mars chain also use the Terra non-standard one? Because I think that's, well, you know, if Mars also used 330, that would solve the problem, right? I think that's the wrong decision. It may make airdrop a bit more smooth in the short term, but in the long term, it creates bigger problem for interchain UX. I'm a strong believer that every Cosmos chain should all use the same 118 coin type, and I think Mars should take the right path instead of sticking with Terra's wrong decision. So that's my opinion. Okay, so since let's just assume Terra accounts and Mars accounts are completely uncorrelated, and when claiming an airdrop, the Terra user needs to specify an unrelated Mars account to receive the airdrop. So how do we do that? Well, the idea is this. So in order to claim, so the normal way of claiming an airdrop is you must provide this parameter. If you look at my screen sharing, I just made this bigger so for you guys to see. For a normal airdrop, what you need to do is to provide this parameter called a Merkle proof to prove you are entitled to a certain amount, right? So that's normal stuff. I'll explain this a bit more in depth a bit later, but this is what you typically need to provide in a normal airdrop. But for Mars airdrop, you need to provide two more things, which is your a Mars account address to receive the airdrop, and this is the important part, a signature signed by your Terra private key to prove that you are the rightful owner of that Terra account and you intend the airdrop to be received by this Mars address. So this signature proves that. So when we do the airdrop, we verify two things. We first verify the Merkle proof, which proves that the provided Terra account indeed entitles a certain amount of Mars tokens for the airdrop. And secondly, we verify the signature, which proves that the person who sends the transaction is the rightful owner of the Terra account, and the owner of the Terra account intends for the airdrop to be sent to the Mars address provided. So basically one extra step compared to other airdrops. So that's a lot of content. Let's give it a brief pause and I look at your question. So there's a discussion on Twitter about coin type, and it was kind of a security so people can find our address on different Cosmos chains. So that is the opinion of Secret Network because they want privacy. So what they want is, if say I have a Cosmos Hub address and that is doxed, the idea is people should not be able to trace my secret network address just from my Cosmos Hub address, which is possible if both networks use the same coin type. Now, secret networks has a good reason for believing that, because they are a privacy-oriented blockchain. That's fine, but for things that, for applications where privacy is not a super big concern, I would say more often than not, we find ourselves in need to know the address of a different chain instead of not being able to know it. So like one of those examples is what we're doing now. We're doing a cross-chain airdrop, right? We have Terra addresses and we want airdrop to Mars addresses. That's a cross-chain airdrop. That is one case where we do want to derive your address on a different chain. And I think this kind of cases is much more often than what secret networks they envision. So I would support all chains use the same coin type. And also, besides coin type, there's a different parameter in BIP39, which is called the index. So your first account is index 0, your second account is index 1, etc., etc. If you really don't want people to trace your different accounts, you can just change different indexes instead of changing your coin type. I think that makes much more sense. Can you provide the proof using Ledger Wallet? Yes. So proof is generated. Proof is, if you know the data, you know the comprehensive list of all the user addresses and their amount, you can generate the proof. You don't need a crypto wallet to do that. But for the signature, you need a proof. You need your crypto wallet to sign a signature. And it just happens that Ledger does not support signing messages, signing like arbitrary text rather than transactions. Ledger only supports transactions, doesn't support arbitrary text. So if you use a Ledger on your Terra account, that would be a little trouble. We have a workaround on that, which we will publish at some time before the airdrop. So that is a Ledger issue. That's a huge, I would say, design mistake on Ledger's part. And it is not something we can fix. Okay, let's look into the code. So, for the beginners here, let's just talk about quickly what's the structure of a CosmWasm contract. So, a CosmWasm contract first needs to define these message types. So there are a few different messages. So if you are from Ethereum, these are basically the contract interfaces, right? So these are, if you want to interact with a contract, say if you're a user wants to send a transaction, or if you're a different contract that wants to compose with this contract, you need to define these so-called messages. So these are the data you need to pass into a contract in order to interact with it. So we have a few ones here, like instantiate message. This is the data you pass into a contract when you deploy a new contract. There is the execute message. So these are transactions that will alter the state of the contract. So the contract might store internally some data. If you want to alter those data, you need to do an execution, and you pass in an execute message to achieve that. So if you just want to do some computation on the contract data, but you don't want to change anything, you can do that through a query message, which we have a few here. There are a few other message types, such as migrate message. That is when you want to upgrade the contract's binary code, you use a migrate message. And there is the pseudo message, which I don't think anyone uses, but it's quite useful. Pseudo message are data that can only be passed into the contract by other Cosmos modules of the L1 blockchain. So only L1 blockchain can invoke pseudo messages. Normal users or other contracts can't. So we talk about that later. That's a very interesting topic, actually, but not quite relevant for today. So for queries, if you query the contract will return you some data, right? So we also needs to define the response types of those return data, which we have here, config and claim. So those are return types for those queries. So we have our messages defined. Next step is we need to define the so-called entry points. So for each message type, we have an entry point. So what's the deal with entry point? So when you broadcast a message, let's say including an execute message, you send that message to the CosmWasm module of the blockchain. The CosmWasm module then locates the contract that you want to interact with and pass in your data to the contract. And that is where the module will look at the endpoints. So if your message is an instantiate message, the contract will pass in that data through the instantiate entry point. If it is an execute message, the module will look for the execute entry point and pass in data through that entry point. And it's really simple. You just create a function, let's say called instantiate, and you put this decorator here called entry point. That will basically declare this function as an entry point. And because its name is instantiate, it becomes the instantiation entry point. So if you instantiate the contract, you pass in an instantiate message, the WASM module will basically invoke the instantiate entry point and pass in those data. So that's it. That's about entry points. So also, if you see that execute message here is we don't only have one execute message. We have multiple execute messages for multiple functionalities. So it is not a struct, it's an enum or enumeration. So we have two enum variants here. We have claim, which is where a user claims the airdrop. And there's the callback. So we only have a limited time span to allow users to claim. So if the user doesn't claim for, say, in 6 months, we are going to take back those tokens and put them in the community pool. So that's the idea. So we have two execute messages. And in the execute endpoint, we are going to basically look at the message. If it is of the claim variant, we have a claim function to handle that. So we invoke the claim function. If the message is of the callback variant, we invoke the callback function to handle the action. And the same, well, this is your claim function. This is your callback function. Same thing goes with query. We have a number of different query messages. And once the data is passed into the query endpoint, we take a look at which variant that query message is. If it is config, we have a function to handle that. If we have a claimed message, we have another function to handle that. So et cetera, et cetera. So that is basically the overall layout of a typical CosmWasm contract. So let me give a pause to drink some water and you guys can ask questions. And by the way, you can join the voice channel, just unmute yourself, just talking to the mic instead of typing. Are there any questions? I see someone is typing. How does the ledger workaround work? So essentially, you need to import your ledger mnemonic phrase, the so-called recovery phrase, into your Terra Station wallet. So that's it. So your Terra Station wallet will generate the same Terra address as if you're connecting via ledger. So that's basically it. When you initialize your ledger hardware wallet, you get a recovery phrase, right? That is your mnemonic phrase. You just need to import that into Terra Station. Okay. All right. So let's take a look at the logic of claim. Let's jump to the claim function. So as mentioned before, to claim, you need to provide your Terra account, the amount you want to claim, the Mars account that you want to use to receive your airdrop. That's three basic things, and two proofs. A Merkle proof, proving that you are indeed entitled to that amount you declared, and a signature proving that you are the rightful owner of the Terra account and you intend to receive the airdrop via the Mars account that you provided. So we do a few things here. So first of all, we check that you have not already claimed. You can't claim twice, right? So the way we do that is we have a variable which we store in the contract state called claimed, which is your Terra address plus the amount. So if you have not already claimed, this data should be empty for your Terra address. And in that case, we allow you to claim. But if you have already claimed, this data should have saved your the amount you claimed. And if that is not empty, we will reject you because you can't claim twice. So we use this update function. So the way update function works here is if the data exists, it will return an option. So if you don't know about Rust, you don't have a good foundation of Rust language, you might be able to find it hard to follow here. And I really can't go into every detail of how Rust works. So I'm afraid you have to have some foundation in Rust. But option basically means something exists, and if it exists, it is of this value type. If it does not exist, then it will be a none. So yeah. So here what we see is if the data exists, is a sum, we throw an error because you already claimed. If it is none, it is nothing. Okay, we save your amount into that data, so you can't claim twice from now on. So that's how it works. And then we verify the signature. If the signature is invalid, we return an error. We're going to take a look at this function very, very soon. Next, we verify the Merkle proof. If it is not valid, we throw an error. Okay, so if both are valid and you have not already claimed, that's fine. We're going to send you the coins. So we compose a message. So that is a bank send message to your Mars account of Mars token of the specified amount. We also emit an event which helps like off-chain apps to index transactions. We create that event, and we put the message and the event into the response. So once the execution is finished, the Watson module will look at the response emitted by the contract and execute the messages, which will send the tokens. So that's how it works. So any questions so far? Again, if you have questions, just jump in the voice channel and interrupt me. Feel free to do that. All right, so if no, then let's look at these cryptography functions. All right, so let's look at the signature. So a signature, so the way the signature works is you have your account's private key and you have a message. The message is basically a text and you sign it. It generates a signature. So that's it. So the message we want people to sign, we define it here. So the message says, airdrop for this Terra account of this many Mars tokens shall be released to this Mars account. So you need to sign this message, right? So let's say the user signed that and provided the signature to the contract. So what do we need to verify that? We need the original message that was signed. We need the public key of the account that signed the message and the signature. Now, here's the first thing. Instead of signing the actual message, we sign the hash of that message. And the reason for that is the signing algorithm only works for fixed length data. So you can only sign data that are of a certain length. But obviously the messages can have different lengths, they varies. So we first hash it, that basically converts the message into a fixed length variant. So we take the SHA-256 algorithm, we sign the message. By the way, this is just how hashing works in Rust. It doesn't make a lot of sense, like what is chain or finalized made, but that is how you hash a thing in Rust. And then what need to convert the signature into raw binaries. So there are different encoding algorithms to convert raw binaries into strings. One of them is hex. The other one widely used is base 64. But here we use hex. So we have your signature, we decode that using hex, and we get the raw binaries. And you can see it's a vector of 8-bit unsigned integers. That's your raw bytes. The same goes with your public key. Your public key is passed into the function in the form of a hex encoded string. So we decode that into raw binary. And we invoke this function called from the API module provided by the Watson module. So this is the name of the signing algorithm, SEC256K1. We just invoke that function. The function can either fail, in which case we throw an error. That means your input data is invalid or whatever. If it is success, it will either return a true or a false, which we return here. So, we verify the signature. If it fails, we use the question mark to throw an error. If it is success, we make sure that it is true. If it is false, we throw an error. So that's how signature works. Any questions here? You are breaking up. Can we go back to SHA-256? Okay, where do you update the map of people who already claimed in your claim method? That happens here in the update function. So what this update do, what this update does is essentially this. So we first load claim. We first load this, right? You write your address. You load your address, right? If claim is true, if claimed, okay, so let's main load. If claim is some, return error, right? Otherwise, we save and your amount. So this is what you want to do. So you load the claim data. If it is not empty, it does contain some data. That means the user has already claimed. Then we throw an error. Otherwise, we save that amount into the storage and we proceed. So this is a more complex syntax. The bunch of things I wrote here are basically the same thing. So you use the update function, you pass in an action, right? So these are the same thing. I just personally prefer the update function than these syntax, but they're the same thing. Okay. So where do you check if the user is claiming the right amount of tokens, not more or less? That is part of the Merkle proof that we are going through very, very soon. But yeah. Okay, let's talk about Merkle tree. Let me first Google an image of Merkle tree so that it's easier to understand. All right. Save this file, save this picture. Okay. You guys see it? Okay, so this is the picture of a Merkle tree. I don't know why it's getting bigger. Better. Okay. So Merkle tree is a data structure that looks like this. So let's say you have a data set. Wait, there's one more question. Let's see. When the user claim, when are you update the map to say the user claim? The method you explain is just to check if the user already claimed. So if you return the amount at the end of this method, the contract storage will be updated to this value. That makes sense? So if I return the amount here, that will update the claimed variable to this amount. All right, okay. So for the airdrop, we have a data set. So data set has a bunch of data points. Each data point is the Terra user's address and the eligible amount for that address. Let's say we have 30,000 such data points. And we organize these data points in a Merkle tree. So on the very top, it is called the root of the Merkle tree. And at the very bottom is called the leaves of the Merkle tree. So each leaf will be a data point. So let's say L1 is the first Terra address and the eligible amount. L2 is the second Terra address and its eligible amount. So what we want to do is what we don't want to do is to upload the whole 30,000 data points data set onto the blockchain. That's not feasible, too expensive. So what we want to do is to generate a very small fixed size signature of this whole data set. We just upload that one signature. Well, let's not use the word signature. Let's use the word fingerprint. So fingerprint, we just upload that fingerprint onto the blockchain. So a very small amount of data, but anyone can use a proof to prove to provide a proof, and that proof combined with the fingerprint can prove a certain data point is indeed part of the data set. So, so how is this tree constructed? So let's say we ordered all these data points in a straight line, like this. So we take them, every two of them as a group, right? Well, first of all, we hash each leaf so that they are of fixed size. And we take these hashes, two in a group, we concatenate them together. So as you see here, hash 0.0-0 plus hash 0-1. So we concatenate them together. And we hash it again. And we derive at this node. For the second group of two, also we hash them each so that they are fixed lengths. We concatenate those two hashes and we hash it again. We get this node. And for these two, we do the same thing. We concatenate them together and we hash it. And in this example, we only have 4 data points. So right now, after 3 hashes, we arrive at the, actually 7 hashes, we arrive at the one single hash, which is the root. So this is the root where we upload it to the contract in the instantiate message. This is the Merkle root. So now the question about, so the thing, let's say why it is called a fingerprint. So let's say you're a bad guy. You change one of the leaves a little bit. You just alter the data a little bit. Let's say maybe you're the owner of this Terra account and you want to claim more than what you're actually entitled to. So you change your amount here. That will change this hash, and therefore will change this hash, and therefore will change this hash. So you make any minor mistake in any of the leaves, the root will change. So that is why we call it a fingerprint, right? Because each data set has a unique root hash. So that's the first question, why it is called a fingerprint. The second question is how you prove that your leaf is part of the data set. So let's say you are the owner of the Terra account in the second leaf, L2. You want to prove that L2 is part of the data set. So what's required here is you already know the full data set off chain. So we can't put this whole data set on chain, but we can put it off chain, no problem. So you have this data set off chain. You see, my leaf is here in the data set, second in the position. I have the hash right here. Can you guys see my mouse cursor, by the way? Because I use mouse cursor to indicate what we're talking about. I assume you can. So you have this hash of the L2, and you know the leaf that's paired with L2 is L1, and you know what data is inside L1, so you know this hash. So the first element in your proof is the hash of L1. So you need to provide this, and you hash this too. You arrive at this node right here, node 0. So once you have node 0, because you have the whole data set, you know that in the Merkle tree, hash 0 is paired with hash 1, and you know the value of hash 1. So you need to provide the hash of hash 1 in your proof. And from those two, you arrive at the top hash. So basically, your Merkle proof will be an array or a list of hashes. In our particular case, if we want to prove L2, our proof would be first element in the array is hash 0.0-0. Second element in the array would be hash 1. So our proof is the array of these two hashes. So let's say another example, if we want to prove L4, right? The first partner with L4 is the hash of L3. So that's the first element in our proof. Then we arrive at here, hash 1. The partner with hash 1 is called hash 0. So the second element in our Merkle proof is hash 0. And between these two, we arrive at the top hash. So the proof for L4 is basically an array of two hashes, the first being hash 1-0 right here, the second being hash 0 right here. So if you have this array of hashes, you can prove that a certain data point is part of the data set. And now we said that the data point, each data point is an Terra address and the amount. So you can prove that. So basically, by doing this, you prove that a certain Terra account is entitled to a certain amount. So, and also we actually define the leaf here. So the leaf is a string, basically your Terra account colon the amount. So that is the leaf. That's basically what Merkle tree is. So let's go back to this question you had before. What happens if signature fail? Then if signature fail, we just reject the whole thing. You can't claim with an invalid signature. Then the user can't claim the airdrop even if he didn't receive it. Yeah, I mean, if you if you do own the Terra private key, then you for sure will be able to generate a valid signature. So that shouldn't be a problem. Okay, so let's take a look at this verify proof function. Okay, so as mentioned, the first thing is we have a leaf is to hash that leaf. So if we go with L2, we need to get the hash 0-1 right here. So we use SHA-56 to hash the leaf. Yeah, we also need to assert that the hash is of the correct length. It's just a minor detail of how this thing works. And now we have hash 0-1. We're going to go through each element in the Merkle proof array. So this is basically Rust functions say to go through each element of an array. So we first grab the first element of the array. Of course, the proof is text encoded. So we first decode that into raw binaries. We concatenate the two hashes as you are seeing here. So we concatenate hash 0-0 and 0-1. Here the thing is, when we concatenate, one of the hashes come first, one comes second. They need to be in a deterministic order in order for this to work, right? Because if you put 0-0 first, 0-1 second, you get one hash. You put the two the other way around, you get a different hash. So we need to define an order. So basically what we do is we compare the hash and the Merkle proof. We just put the smaller one first. If hash is smaller, we put hash first. If the proof is first, smaller, we put the proof first. So that's the order. So, and then we concatenate the two hashes and we hash the two things together. So that will give you hash 0. And then because it's an iterator, so we go into the second iteration, that will grab the second element in the Merkle proof array. So now we have this, and the second element of the Merkle proof array is hash 1. We do the same thing. We decode the proof elements, we concatenate them, and we hash. So right now we should have arrived at the root. So here, Merkle root. This is the Merkle root stored in the contract storage, which we provided during instantiation. We grab that and we decode that into raw bytes. And here we assert that the Merkle root stored in the contract store is the same as was derived by the Merkle proof and leaf. If they're the same, then the Merkle proof is valid. That proves that this user indeed has this amount of tokens entitled in the airdrop. If they're non-equal, then the proof fails. We do not let the user claim in that case. Okay, so that completes a chunk of content. If you have any questions, please ask. But for now, you can see I have a bunch of test cases in the testing right here. We have a root. So this is a valid proof which passes the test. Here is an invalid proof. It is generated if, let's say, one of the users attempts to claim a different amount. So they insert a different amount into their leaf. So in the Merkle tree, this user is entitled to 42069 tokens, but the user changed that to 6940. That is the mutated leaf that gives a different Merkle proof, and that does not match with our root stored in the store. So that fails. And the third one also, the user forges a false Merkle tree, and that also fails. So yeah. Yeah, any questions? How do you generate the Merkle tree from the data? That's a good question. So that is generated on the front end. So I have a script here actually. So we're going to use this JavaScript library called Merkle tree.js. This is our Merkle tree, right? So each leaf is an address and the amount. So we convert each of these data points into a leaf, which is the string, right? Your address colon your amount. And then we just use this Merkle tree library, right, to generate the tree. And we just call tree getProof. So getProof takes the leaf for which you want to generate the proof for, and that generates the proof. So yeah, we just use this JavaScript library, which this whole thing is going to happen on the front end. All right, let me drink some water, and we move on to the next section, which is callback. This is the interesting part because we actually had to make some modifications to the Cosmos SDK in order for this to work. But let me have some water first. All right. So, okay. So callback. So during the instantiation, we provide a parameter called claim period. So these are the number of seconds that the user have to claim. So during instantiation, we grab the current block time plus the claim period. So that's basically your deadline. You must claim before this time, right? And we save that in the storage. So during callback, so this function is can be called by anyone. So we grab the current time and the deadline stored in the storage. So if deadline is not yet, we do not allow a callback. If deadline has passed, then we query all the tokens that currently the contract holds, and we donate that to the community pool. So we use a message called found community pool to donate this whole amount into the community pool. So this block here, this basically parses the array of coins into a string, so we can put that into the event output. So we create this message, found community pool. We create an event and we emit the response. So it's pretty simple here. So the difficult part here is the custom message. So why do we have to use a custom message? Well, if you look at, okay, so it turns out that donating funds to the community pool is not as simple as just sending token to the community pool module account. So if you don't know, Cosmos SDK has this thing called module account. It's basically equivalent to Ethereum, where you have smart contract accounts. So you have two types of accounts. One is called the base account. So these are accounts that are controlled by a private key. So this is called base account in Cosmos, or externally owned account, or EOA in Ethereum. So that's one type. The other is accounts that are controlled by computer code. In Ethereum, this is called a smart contract account. On Cosmos, it's called the module account. So the community pool is controlled by a module called the distribution module. So you might think, hey, the community pool is just the distribution module account. But that's not how it works, because the distribution module account does not only hold the community fund, it also holds the unclaimed validator commissions and staking rewards. So when you claim your staking reward, what happens is you go to the distribution module and withdraw some amount from tokens held by that module account. So in my opinion, it is actually cleaner if the distribution module can just put these three types of funds into three different module accounts, like one for community pool, one for commissions, one for staking rewards. But I'm not the developer. They decided to put them into one module account. Who knows, whatever reason, but that's what they did. So because of that, you cannot simply just send the funds to the community pool module accounts. You have to use a special message called the fund community pool message. Actually, let me just show you guys here. All right, so this is the Cosmos SDK repository. So we discussed before that for smart contracts, the interface is defined by the messages. For SDK, it's the same. They're defined by messages, and they're in this folder called Proto. So Proto contains these so-called protobuf files. Protobuf is basically a programming language for messages. Right? So look at distribution module. We want bit one. So the messages are defined in the transaction.proto file. And we see here they have a function. So this is their message service, and these are the message types. So one of the message type is message found community pool. And if we look at that, that contains the amount of coins you want to send to the community pool and the address of the depositor. So basically, we need to provide this message in order to fund the community pool. However, CosmWasm by default does not support this message type. So if we look at so these are what Cosmos SDK, what CosmWasm by default supports. They support bank messages. These are messages corresponding to the bank module. These are messages corresponding to the staking module. This is what corresponding to the distribution module. And if you look at the distribution message down here, where is it? Here. It only supports two, set withdrawal address and withdraw delegate reward. So basically things related to staking rewards. So if we go back to the Cosmos SDK message types, we see here is the set withdrawal address, here is the withdrawal reward. There are three others that it doesn't support. So that's a problem. So what's the solution here? Well, we need to define a thing called the WASM binding in our blockchain's code, which I'm going to show you guys right now. So you see, I have two repositories here. One is called Hub Periphery, which are these smart contracts, and the other is called Hub, which is the actual code of the blockchain. These two repositories are both open public anyways, by the way, so you can take a look at that. In the app folder, we have a folder called WASM. So this is where we define the bindings. So let me save them first. So you want to define a function called register custom plugins. So there are two types of plugins. The first is the message handler, which corresponding to execute messages. And there's the query plugins, which corresponding to queries. So these are just boilerplate code, which you just copy from the core WASM repository. So don't have to worry too much about the specifics here. But the thing is, we need to create this thing called the message handler decorator. And the message handler decorator requires a number of so-called keepers. So keeper is a concept used by Cosmos SDK. So keeper is basically a bundle of functions to read or write data from a specific of a certain module. So here we want to write data at the distribution module, so we need to use the distribution keeper here. So let's look at this. Let's look at the message. So, okay, so the first we define our custom message type, which is called, I call it Mars message here. I want to support the found community pool message. That's the only one I want to support. So this is the only one I have here. And the found community pool message contains the amount parameter. Previously, we saw there is a second parameter called the depositor, but we don't need it here for reasons you will see shortly. So when this is defined, we go to the custom message decorator here. So again, these are just boilerplates. You don't have to worry about them. The one you do want to worry about is these two functions. So once our contract has emitted that custom message, the WASM module will say, hey, it is a custom message. For custom messages, they will send that message into this dispatch message function. So this function will basically go over all the supported custom message types and see which type is it. So what we do here is the message here. The message here is by the way, raw binary. We first need to parse it into our Mars message struct. So if it is of the found community pool variant, we dispatch that data into the found community pool function right down here. Now we only have one type, but if you have another types, you need to keep writing. Like if Mars message is something else, right? You dispatch that to another function. So, but we only have one, so that's it. So inside this, we go to the distribution keeper, we create a message server. So message server is basically another object, another bundle of functions that can handle transactions. So what we do here is we basically translate our custom Mars message, which is defined here. This is our custom Mars message. We translate that into the distribution module found message community pool message. So remember I showed you a protobuf file for a while back. This is the protobuf message defined in that file. So we have an amount, which is the amount defined by my custom Mars message. And for depositor, we simply use the contract address. So this is why we don't have to specify the depositor address here in our custom message. So then we are going to execute this message. Once we translated that into the distribution message, we're just going to execute this message. And if there's no error, all fine, we just call it a day. If there's an error, we return the error. So that's basically it. So go back to our contract. Sorry, there's a mosquito. Go back to the contract. All right, wait. Before going back to contract, let's see how we incorporate this custom binding into our chain. So our chain is basically a bundle of bunch of keepers. So there's a keeper for everything. Like for governance, there's a gov keeper. For distribution, there's a distribution keeper. For IBC keeper, WASM keeper, etc. So when we define WASM keeper, there is a parameter called WASM options, and inside these options we append the custom plugins, which are our message binding and query binding. We append them to the list, and when we create the WASM keeper, we put that into the options. So now the WASM keeper knows our custom handler and is able to handle that. So that's it. Back in our contract, so you see I define here in the airdrop contract, I have a message. I have a file here that defines the custom message. So if you look at this file and you look at this file, so they're basically the same thing deployed in implemented in different languages. So you have a Mars message, you have one variant from community pool, and that one variant has a parameter called amount. This is the same thing in Rust. Basically, you have Mars message with one variant from community pool, and that one variant has a parameter called amount. So yeah, so this amount in the SDK code is of the type coins. In the Rust is a vector of coin. So same thing. So in order to use this Mars message as a custom message type, you also need to implement a trait called custom message, which is provided by Cosm Volume STD. But there isn't anything to implement, so so it's empty. Yeah, so what custom message does is basically impose some requirements, like the custom message must be able to serialize, must be able to be cloned, compared, and have JSON schema. So yeah. So that's about it. And in the contract, when we emit this message, we use the custom variant. And in the custom variant, we inject the Mars message type. And we specify it is to fund the community pool, and this is the amount. So I think that concludes this part on callback and related modifications we did to the SDK. So any question here? Any questions here? You can feel free to ask. If no, I guess we can, that's actually pretty much about it. We can perhaps look at query message where there's nothing interesting really. I think what's one thing we need to mention is, I tweeted about this before. I think every map data structure, so if you have a map here, it's my opinion that every map data structure should have what I call an enumerative query function. So basically, it allows you to, instead of querying one individual element in the map, it allows you to enumerate all elements of the map. So it's called an enumerative query function, and I indeed have one here called all claimed. So if you query claimed and provide a Terra account, it will tell you how much token this account has already claimed. But if you don't have a particular account in mind, you just want to know everybody, you can use this all claimed query. So obviously we have 30,000 different accounts, so we can't return all of them in one query. So we need to use these pagination parameters. So start after specifies so we have, let's say we have 30,000 accounts. They are ordered alphabetically. Let's say you have queried first, you have queried it once without specifying start after. It gives you 10 results back. And in the second query, you want to start from the 11th. What you do is you put the last result of the previous query as the start after parameter. Then the second query will start after this result. So that's basically how pagination works. So this is basically a boilerplate code on how to write an enumerative query function. You use the range method to grab an array of results. You take a number of bits, which specify the limit parameter. You parse each of them to the response type, and you collect them into an array. So that's how you do the enumerative query. I think this concludes this session. I have already discussed everything interesting about our code. Let's see the question. How do you pass the Mars WASM plugin modification into the validator network? Or when the Rust compile the result is on the contract WASM file? So the WASM plugin is not part of the WASM file. It is part of the marsd executable. So, you know, each blockchain has an executable client, right? So if you run a Terra node, you need to download the source code of Terra and compile a software called TerraD or Terra daemon. For Osmosis, there's the Osmosis daemon. You compile that from the Go code. For Mars, we have marsd. So marsd is defined here in the hub repository. So your WASM plugin is part of the marsd logics. So it's not part of the smart contract, it's part of the blockchain L1 executable. So each validator will run the marsd, right? And so they have that logic. All right, so that's it for today. Next week, I think we'll talk about the vesting contract and some modifications we made to the SDK to accommodate the vesting contract. So I think that will be much more interesting than today's topic. So that's it for today. If you don't have any questions, feel free to leave. If you have questions, type in the chat or join the voice channel. And thank you for joining.